Hello and welcome. Today I'll be talking about the kinetic limitations of the floating catalyst carbon nanotube synthesis process. Motivation and background for this project: carbon nanotubes have outstanding properties. Their macro assemblies can now outperform carbon fiber and copper in certain applications. So really the problem comes with the scalability of the synthesis techniques. FCCVD is one of the most scalable routes for the synthesis of CNTs and reforms methane to a high quality material. However, the process suffers from low production capacity and poor catalyst utilization. So for the FCCVD process to become a viable solution, we must be able to densify this reaction. So looking at figure 1 on the right, logically speaking, if you increase the carbon mole fraction, you will be able to form more CNTs, and in order to do so, you also need to increase the total catalyst mass. So the question really is how far can we go along this graph? And empirically speaking, we found that in a hydrogen atmosphere, people like to work in around about 4% carbon mole fraction input. To investigate the limits of the FCCVD process, we propose a collision-based framework in order to study the problem. The first collisions are between the synthesis ones, so the formation of CNTs from the collisions of acetylene and the iron particles. We then had a look at particle collisions because the FCCVD process is an catalyst inactivation diameter beyond which CNTs don't grow. And finally, we looked at the most probable soot-forming pathways. So mapping all of this out onto the ground scheme, we found that the synthesis zone is bounded by 3 regions. First region being the iron-rich zone, in which you have too much catalyst mass, your particles coarsen far too rapidly, and you effectively are not able to form CNTs. The second zone is limited where you will have soot production formation, and this is where you don't have enough catalyst, so effectively if you put in too much carbon, you're just going to form soot instead. And finally, the most interesting zone, zone 3, this actually provides a fundamental limit to the FCCVD process. So particles reach a self-preserving size distribution, and when they continue to coagulate beyond that size, effectively they become inactivated. So if you put in too much catalyst mass, your particles grow beyond that size, and you are unable to form those CNTs. So in conclusion, physical upper limit now exists for the formation of carbon nanotubes in an FCCVD reactor, which is around about 8% carbon mole fraction and in the hundreds of milligrams per meter cubed of iron. Coagulation of particles limits the process, so once they reach a self-preserving size distribution, the final particle diameter is affected by the total particle volume and number distribution. And increasing the number of nanoparticles releases into a higher collision rate. However, the fraction of active catalyst significantly decreases, resulting in an upper limit to FCCVD.